There you go. Got it. And again, I forgot to include the link from last week. So if you really wanted to see it, remember, contact me so I know that you want to see the links and have access to them. So let me take this off and continue here. So I wanted to write just a simple loop to do the standardization of all the variables. For the loop, in this case, I'm going to use a for each loop. What I'm saying here is for each I, this is the variable that will change the names. In the list, all the variables that I want to add to the model, do the following. What is the procedure? It's I first need to estimate the mean and the standard deviation of the variable, so I can just get the summary or summarize the variable. And I'm going to create a standardized version with the same name. That is nothing else than the original one minus the average divided by the standard deviation. So what this is going to do is going to go over the list of all these 4 variables, and each time it's going to replace the value of I or the name of the variable and just create 4 additional variables in this data set. How do you know that they are standardized? If you get the simple summary statistics of those, you will see now that the standard deviation is 1, so the variance is 1, and that the mean of the variables is 0. Here you see something slightly different than 0, just because in computational terms, getting a perfect 0 is almost impossible. So this is as good as 0 as it's going to get using the format of data that I'm using. So now I can rerun my regression, and instead of doing this, even though this is relatively simple to interpret, I'm going to run this other regression. That is now going to constitute my standardized regression. A couple of things to notice. As I mentioned before, nothing changes in terms of the characteristics of the F statistic, of the level of goodness of fit of the model. Things are going to change here because we are changing the scale of the data. But again, the T statistic, the R square, everything else remains the same. The only thing that changes are the coefficients and, of course, the statistics that are related to the coefficients. But the actual value or the actual interpretation of them does not change. Also notice that by construction, my constant should be 0, because all the variables are now have a mean of 0, and the same with all the dependent and independent variables have now a mean of 0 by construction. So this model could actually have also been estimated requesting a data to have no constant. But if you recall what I was mentioning last week, you almost never want to ask or request to have no constant in your models, or at least that's what the books suggest. And I'm also believe that you should almost never use it. But because in this case, by construction, your constant should be 0, you can apply that here. Now, how do we interpret these coefficients? The interpretation should be what happens with the distribution of log of wages when there is a 1 standard deviation increase in education. So, for example, if there is a 1 standard deviation increase in education, your wages should increase in about 0.35 standard deviations. If there is a 1 standard deviation increase in tenure, your wages are going to increase in 7.8 standard deviations. If your age increases in 1 standard deviation, your wages should increase in 0.28 standard deviations. Now, again, for some fields, not necessarily in economics, this interpretation makes things easier, or this way of using the data makes interpretation easier because everything is measured in the same units, dependent and independent variable. So I can, for example, compare the results of the coefficient of education and see that it's actually the most important component or the most important variable to explain the variation of wages. That's why the coefficient is 0.35 compared to 0.28 from age, or 0.08 from tenure. Now, as I was saying, this is the case. However, it's not necessarily easy to interpret if you are in economics or you want to explain this to somebody who likes the actual measures of the data, because we do not know what exactly it means to have a one standard deviation increase in tenure, or what it means to have a standard deviation increase in education, or a standard deviation in age. And it's going to be even worse if I decide to include something like female. What does it mean to be one standard deviation higher being a woman versus standard deviation lower of being a woman? In those cases, it has no interpretation whatsoever. So for you ever encounter only beta coefficients, something that you might have to rely on, for instance, would be to look at the original distribution and try to figure out what exactly it means to have an increase in tenure, education, or age. So, for example, when I say what happens when there is a one standard deviation of education, what I'm really saying is what happens if, in average, a person increases its level of education in 2.4 years. Or in terms of age, what happens if a person becomes 11.03 years older? What's the impact on their wages? And now it makes sense why we have these relatively large changes in the coefficients when we try to interpret it on the impact of our dependent variable. By the way, were you able to see what I just showed you on this data? Hello?
I could see it.
Okay, I wasn't sure because I was still having my presentation up.
I have a big screen, so Zoom does a weird thing. It wastes too much space on everybody's beautiful faces and doesn't give you much room to look at the.
All right. So now you should be back again to the presentation. Another example, and here we're going to use this data of pollution. In this case, the idea was to figure out how the prices of a house could be affected by some amenities where the house is located. Specifically, we are trying to see whether the price of a house is a function of the level of contamination measured by the level of what's NOx. It was, let's check that out because I don't remember what the NOx is. Rios H price 2 clear describe NOx prime in the rooms price distance and ST ratio. Okay, so this is information at the regional level. I'm guessing you all can see my data right now. Yes?
Yes.
Thank you. So because this says this is median prices, I'm guessing that this information is at the regional level. And at the regional level, the other piece of information that this is trying to say is whether the price of the house or the median price of a house in a particular region is a function of the nitrate of oxygen. It's a kind of pollutant, air pollutant. The concentration of that per 100, not sure what N would be, but let's say the concentration per 100 square feet of air. The number of crimes committed per capita, so how many crimes per person are committed on a specific number of times or in a specific period of time, the average number of rooms, the distance, the weighted distance, because you have many houses in the region, but the distance to the 5 closer employment centers and the average student-teacher ratio, so a measure of the quality of the schools in the area. So if I give you something like this and I ask you to tell me what do you think of the expectation regarding to the different explanatory variables, what would you say? For which one you should expect a positive and for which one a negative effect on the prices of the house? This is where your economists have to come up.
Crime would be negative, rooms will be positive,
Yes.
and does it district?
This one?
Yeah. Wait, distribution?
Distance, the closer,
Distance.
the closer, the better, right?
Yeah, it will be positive.
Yes, it could be that the closer to the deployment center, the better, because you have to pay to be closer to the city, correct? Although you might also argue that is the other way around.
Well, it'd be probably some median distance that would make sense. You don't want to be in an industrial district normally, but you'd want to have a short commute. So you'd want to be in Rye relative to Manhattan.
Yes.
Rather than Rhinebeck, for example, which probably Rye has double the property values of Rhinebeck, believe it or not, right, or something like that.
So probably we should be mindful of that when we actually start modeling.
Probably be more like a geometric relationship than a linear one.
Yes, exactly. But for now, we're going to still assume that the effects are direct. And for contamination, you should expect as well that the higher contamination, the lower the price, because you want to be compensated to live in an area with a lot of pollutants. And finally, school ratio, probably you're going to pay more if you're in a better school area, in a better school district. And assuming that better school district means more, actually, this is the other way around, the student per teacher ratio. So the higher is this, the lower you would be paying, because it means there is a lower quality of education, most likely. That's why there is more students per teachers. Okay, so given that, do the coefficients actually make sense on that regard? Apparently it does. Pollutants have a negative effect on prices, same with crime, a number of crime and the student-teacher ratio, which calculates the inverse of the quality of education. Number of rooms as expected, larger houses, you pay more. So that's reflected directly on the results. And distance, it's a negative effect because the farther that you are, the less likely is, or that you want to pay you don't want to pay the premium for living close to the employment centers. So given that, and if I give you nothing else, even though you can make this kind of interpretation of the results, meaning the direction and the expected explanation of the effects, it's a little bit harder to explain which one of these is the most important factor that explains the variations of prices, and B, how much, what does it mean to have an impact of minus 153 or minus 2,707? Because we do not really know, or at least most of us will not have an idea of what should be a good range for NOx. Should we expect this to vary in thousands of units or just in percentage units, in decimals, etc.? So instead of doing this, I could estimate the beta coefficients and interpret those instead. So here, I would argue that it would be a little bit more reasonable to interpret this coefficient because it makes more sense to talk about pollution and whether or not the pollution is increasing in one standard deviation compared to the current level. The same with crime. Are we expecting crime to increase, or if we expect crime to be one standard deviation higher or lower? For rooms, again, I would prefer to keep it as in units and not in standard deviations, but in this case, we're going to just use the standardization, distance, and the teacher-student ratio. Now that we have all of these results, you can tell me which one seems to be the most important factor that determines prices of a house. Which one would that be?
Pollution rooms, like they're all, it shows that they're all statistically significant.
But rooms
True.
is the largest, yeah.
Yeah, so all of them are statistically significant, but rooms, once we standardize the coefficients, has the largest coefficient, so it means that it has the most contribution to the variation of the prices. Followed by rooms would be pollution, so that's the second thing that according to this model, people might be considering when deciding to buy a house or to pay for a price of the house. Followed by the student-teacher ratio, so that if you want to think about what is the range of priorities based on this model, people first look at the size of the house, the level of contamination of the area, the quality of the school district, how far it is from the jobs or potential job areas, and surprisingly, the last thing that seems to be related to prices is the level of criminality in the area. This is, of course, assuming that these are completely independent, because it's very likely that the closer you are, the higher the crime, or the closer you are to the employment centers, the higher might be the contamination, etc. So for now, let's assume that these are completely independent, and if that's the case, we can make this assessment of which factors are the most important to explain our dependent variable. Now, again, in this data, even though I showed you a way to do this manually, in the sense of standardizing all the variables first before making the regression, you can also get the same results by just including the option beta. And I call it an option because it comes right after a comma. So when you do this, let me show you that over here. This is the standard output that you're gonna get. Same thing that we had before. But if you wanna get the beta coefficients, you just indicate beta, and all the results are going to be stored here, are going to be showed here. There is no need to include separate measures from the standard errors, t-values or p-values, because the t's and the p's are going to be exactly the same. And also, there is no sense of reporting the constant, because there is no constant when we talk about beta coefficients. Okay, the next step or the next point is to talk about functional forms and the impact of log functional forms or log functions for the analysis of the data. This is something that actually I believe it was Arya who asked last week on why do we want to include logs in a model. And what I said at the time is the usual reasons it's because you want to make better interpretation of the results. Because once you go from a linear model to a log model, log linear model, or linear log model, you can make a different kind of interpretation of your coefficients, going from unit change that assume a linear relationship to something like an elasticity that gives you a little more flexibility in terms of assuming that the relationship is not absolute, but rather relative between your dependent and independent variables. And of course, you also have the points in between when it doesn't really make sense to apply the log transformation either to the right or to the left of the variable. And in this case, for example, would be that it would be convenient to apply logs when your dependent variable is wages and your independent variable is perhaps tenure, that you can talk about how a 1 increase percent in tenure might increase your wages in what percent, but it wouldn't make sense to talk about trying to apply logs to something like, I don't know, to gender, because this is a qualitative variable and it makes absolutely no sense to talk about the logs of this, or perhaps something like education, because education is not going to increase by much. There is only a certain number of range of variables that this could take. Perhaps 25 nowadays. So it doesn't make much sense to apply a log function to this variable. Now, another convenience of using log functions is that the slope coefficients, when you have a log variable, they're going to be invariant to rescalings. And that's the other thing that I mentioned before. When you have a log variable that is an independent variable, or is on the right-hand side as part of the independent variables, it doesn't matter if you rescale the original one, using the log transformation kind of reduces the impact of that rescaling. Another way of thinking about this is that every time that you introduce a log in your model, you are changing from talking about absolute relationships to talking about relative relationships, and relative relationships are typically invariant to changes on the scale of the data that is being transformed. In addition to this concept of these reasons of convenience for interpretation and convenience instead of some of the invariance properties of using logs, you might also want to use logs because it might help you, but again, it's not something that you have to do, but it might help you to eliminate or mitigate problems of outliers. Now, what is an outlier? Outlier is just going to be an observation either on the dependent or the independent sample, or dependent or independent variables, that is way far from the distribution of the other numbers in your data. So the example that Ben was bringing up was, for instance, if we consider the price of housing, let's say in this area, well, around Rhinebeck, the range of prices might be for a house, I'm guessing between $200,000 to $600,000, and probably lowballing it. However, I'm pretty sure that there are some houses in Rhinebeck that are extremely expensive because of the amenities of the area, being close to New York and being an attraction point. So the prices is probably close to the millions. And if that's the case, if you would like to do a regression with that kind of data, those millions are going to heavily impact the coefficients that you have in your model, because it will have a lot of leverage, a lot of weight when you estimate the coefficients. So one way to mitigate that problem, which is not really a problem in terms of regression analysis, but in terms of what you're going to obtain from just applying the methodology blindly, is that extreme values will have a strong impact when you have an outlier. This is going to have a strong impact on your beta coefficients. However, when you take logs, because you're reducing the dispersion of the data, so if this is the actual data, this is in logs, you're reducing the dispersion of the data, you will be mitigating how much weight we are actually giving to the outlier. And the coefficients are going to become more stable, because they will not rely as much on the outlier observation. The other reason, technical reason, but again, not something that you need to do, is that taking logs also helps to improve the normality of the data and the homoscedasticity property of the error. Question: why is it that we care about normality and homoscedasticity on the errors? Anyone? Why do we care about normality of the errors?
For small samples, it was like the assumption that we have to have normal distribution, that for large samples, it doesn't matter.
Exactly. So really the normality is because when you have a small n, you need the beta coefficients to distribute as normal, and normality is the only way to get the coefficients to be normal when you have small samples. When you have large samples, you rely on asymptotic normality, so this doesn't matter anymore. So that's why taking logs might help to get normality of the errors, but it's not needed. Why do we care about homogeneity? Huh? Ben?
Well, so you're using what's effectively a mathematical artifice to reduce the dispersion of variance, right? So in that sense, wouldn't you have to be to some extent careful? I mean, compression, you're compressing the data, effectively you're compressing it. I think of it as an analog to like audio technical stuff, but where you run a compression on a sound stream, basically, right? You're running a compression, basically, right? So in doing so, you're also trimming out, if you run compression on an opera singer, then you lose some of the range of the singer and you lose some of the quality of the audio, is a way of, analogy.
Yes, that's a very good way to make the parallelism. So applying logs compresses the data. The information is still there. But by compressing the data, we are losing some of the variation that is perhaps important that is on the extremes of the data. However, most of the time we're not as interested on what's going on at the extremes. We're more interested in what's going on at the middle of the distribution. So in those scenarios, is that compressing the data, you think in terms of music, for example, is more important because it will give you a better representation of the actual song, even though you might be losing some of the streams. In terms of the data, it might help you to get a better idea what's going on with the conditional means of the data, rather than trying to spend too much time fitting information that explains only the extremes. So that's a very good parallelism of why we want, or we might like, to introduce logs on the model. The other thing is that every time that you use logs on the model, you need to be aware of that by doing that, you're really changing the relationship between the dependent and the independent variables. And that is already explained before, because all the marginal effects are no longer a one-to-one variation, but you're talking about now unit variation versus percentage variations and vice versa. So in this case, when you use a log linear model, log linear because the logs are applied to the dependent variable, what we have done or what we have explained, and probably you have read also in the book, is that it changes the interpretation of the coefficients, because now this beta 1 becomes, if we leave this in units, what this is trying to explain you is in what percentage would the outcome change when there is a 1 unit in X. That's how we were interpreting. For example, in the models of wages, log of wages as a function of education, this coefficient alpha 1 was being interpreted as in how much, if it was like 0.09, we're saying that an additional year of education would increase wages in about 9%. So it was just reading the coefficient, multiply it by 100, and say that that's the percentage impact that you're going to observe on the dependent variable. Now, something that you need to be aware of, and people in other fields are much more strict with this, is that just making that simple transformation of the beta coefficients is incorrect. It's just an approximation, because what you're really trying to do is do something like this. If this is your original model, and you back transform the the outcome to be in levels, this is what you're trying to relate to the changes in X. If we do the trick of X plus 1 and take off the original value, you're going to see that what you actually want to interpret as the percentage change respect to the base, respect to the baseline scenario, is really equal to the exponential value of the beta 1 minus 1. It just happens to be that when this beta 1 is very small, this expression is approximately equal to the coefficient itself. So what does this mean in practical terms? If your coefficient is between 0 to 0.1, perhaps 0.2, and I'm considering both the positive and the negatives, you can simply interpret this in a log linear model as by just multiplying it by 100. Easy does see no changes. However, when the coefficient is larger than this, it's probably better if you apply this transformation over here. Now, how much of a difference that transformation is going to do? So let's do a simple example. Okay, so what I'm trying to plot here is what will be the relationship between the coefficient that you're estimating and the interpretation that we'll be making in terms of the percentage change. This is the approximation, and this is the exact value based on this correct interpretation of the beta coefficients in a log linear model. So if I reduce this, if n is less than 0.2, for the small values, let me also put this. For the small values, the difference between the coefficient, and this is going to be the red line, and the exact coefficient or the exact value is very small. So you would be saying, for example, if the coefficient is 0.1, difference will be between 0.1 and 0.11. So a 0.01 point difference on the interpretation. Even if you go to as far as 0.2, probably the approximation difference will just cause you a 0.2 difference over here. So not much to be concerned about when you try to make the interpretation of the coefficients. However, if we start seeing factors that are beyond, let's say, 0.5, then we're starting to make very important differences on the numbers. Let's consider this scenario. If the coefficient is 0.7 on what comes from your regression, and you will interpret that as 70% higher increase on your on the outcome, for example, it is actually underestimating quite a lot the exact increase that you would expect to see in the outcome. By how much? According to this, almost 30% lower from what the more exact approximation is trying to provide. So again, the lesson, if you think that the beta coefficient is small, just use it by multiplying by 100. You think it's larger than this, probably better that you mention that you're going to use the exact approximation or the exact value of the proportional increase and report that number instead of the coefficient. Especially if you're going to publish in areas other than economics, like sociology or similar areas. Now, something that was being asked last week as well. When should you use logs? Is it correct to log everything in a model? If you go back to my original recommendations, that logs should be used only if you want to interpret the results better, or you want to make a little bit of a changes on the nature of the data, getting closer to normality and also homogeneity. It might seem that you would like to log everything. However, there are some cases where the information itself is better to be left as it is. Which kind of cases? And this is not a hard rule, but something that I in particular believe is correct. If your variable, whatever variable that you're using, is measuring years, for example, age, years of education, years of experience, etc., my preference would be that you shouldn't be logging that variable because you're losing. I think it's better to keep the relationship between years and the outcome as a semi-elasticity rather than create or trying to force an elasticity, because relative changes on education, on age, experience might not be as easy to understand, or at least imagine what exactly they mean. Based on the same idea, if the variables that you have as independent variables or explanatory variables are in percentage points, something like what's the share of I don't know, of Hispanic living in the region, etc., you shouldn't log that variable because you're going to be changing. You're going to try to make interpretation of the percentage change on a percentage, and interpreting those kind of variables becomes much more difficult the more complex your model is. So if something is already in percentage, forget about logs, just use it as it is and figure out how to interpret that variable directly. Next is that logs must not be used if the variable that you're trying to work with has either a 0 or some negative values, because in those cases, the log is not going to be defined. For example, you shouldn't be logging something like the number of children, because otherwise you're going to be losing the information on families that have no children, for example. In parallel, for instance, if you decide to do something like, what's this, standardization or beta standardization to get standardized coefficients, you wouldn't be able to apply logs to the standardized variables because by construction, all the standardized variables, some of them are going to be negative. You should also be aware of that when you apply logs to the dependent variable, trying to reverse the log operation in order to make predictions could be difficult, even though it's not impossible. And I actually go and try to do that. And it's also explained in the book on how to do that for some models. And we will see a little bit of this later. Using quadratic functional forms. Okay, let's stop a little bit. Let's stop here for a little bit and get back in 5 minutes to continue. All right. I would take the silence as a yes. Be back in 5 minutes, guys. Okay, and we're back. So the next thing that we're going to talk about is, and something again we have touched a little bit in the past, is the use of quadratic functional forms. Now, why do we care about including or introducing the idea on quadratic functional forms? As I mentioned last class, or a couple of sometime in the past, is that the main reason why we want to do this is really to add more flexibility to the model. And again, why is that? Because we have to acknowledge that when we use a linear model, what we are really saying is that the relationship between the dependent and the independent variable are strictly linear, and that should be fine for everybody in the population. Most of the time, assuming a linear regression is fine for the means, for the average person. However, extending that to everybody in the population is going to be a very strong assumption. So one of the things that we like to do is to say, let's assume that it's not exactly linear, but it's something else. So let's try to capture that something else, that additional flexibility, and let's add that to the model. And the simplest approach to add this additional flexibility is by using, if I want to go with more technical terms, tailored expansion of second order, which basically means in addition to the linear parameter, you add a quadratic parameter to get some of this flexibility. Now, what you should be aware of when you add quadratic terms is that the coefficients themselves, individual coefficients, are going to now be difficult to interpret. Actually, you cannot interpret them individually unless you do something else with those coefficients. For example, let's assume in this model, and let's actually go and estimate this model manually. If I have this data, the data set is wage 1. So the model that we're now going to try to estimate is wage versus experience. So this is the original model. What exactly this model is telling you? Any guesses? Hello? So what this
We
model
will
is
add education as well.
excuse me?
For the second regression, we will add education as well.
We can add education, but for now we're going to just assume that the only thing that determines wages is experience. So in this simple model, we are just saying that each additional year of experience adds to your wages about 3 cents per hour. That I'm assuming, yes, wages is average hourly earned. So for each additional year of experience, your wages are going to increase in about 3 cents per hour. Now, is a linear relationship enough for this kind of data? As I mentioned earlier, or at some point, either last class or the class before, one of the things that you can do to figure out if the relationship is indeed linear, especially when you have only 2 variables, is to plot the results and see what's going on there. So here I'm just plotting the years of experience against hourly earnings. And what is this showing you? Is the relationship really linear or not? You might say, perhaps it's linear and it's increasing, but I'm not able to capture that. Or it's almost flat, and that's why my coefficient is so small.
Looks parabolic, though, basically, is what you're getting at, right?
You might say that for some people it's parabolic because of this information over here, but it's also possible that these are just outliers, so we do not know. So the point is, what if the relationship is not linear? Can we do better? So this is what we're actually trying to plot right now. You have the dots for the current, that's trying to show you the relationship between wages and experience. And this red line is the fitted values that is a direct transformation or is coming directly from the model that I had before. However, again, is a linear model really, let's see. So would a quadratic model do better? So I use just this graphic tool to figure out if the relation is quadratic. And actually, visually, it seems that it's doing better. And it's actually capturing better it's also capturing this relationship between experience, not only at the beginning of life, but also at the end. So in the first model, we were technically be assuming that it doesn't matter how much experience you're getting, your wages are always increasing, which might be against common sense. In this other case, we will be saying wages increase based on experience at a certain point, and then they start to decline. Or as Ben was saying, there is a little bit of a parabolic increasing but then declining effect on wages. So this suggests to me that perhaps we should give a chance to use a quadratic model. Now, how do we estimate this quadratic model? Now, Stata is very picky with that. If you do the regression, you will have to say something like this to estimate the quadratic model. So what exactly I'm doing is that this pound symbol is telling the Stata I'm going to multiply experience with experience, and that these variables are continuous. So this is how you estimate a quadratic model in the Stata.
So the C is for continuity, basically?
C basically tells a Stata this variable is continuous, because otherwise, if you try to do it without the C's, it's going to try to use every single variable of experience as a dummy, because that's what Stata understands. And that's incorrect. So if you want to use quadratic terms, you will have to always use quadratic, cubic terms, etc. You have to include the C dot. So a state understands that this variable is continuous, and internally is going to create the quadratic term. So now that I estimate this model, and let me compare it with the previous one, how would you interpret the coefficients? So in the first case, I was saying each additional year of experience increases your wages in about 3 cents per hour. Can you say the same with this model? The answer is no, you can't. Because the coefficients, because now we're having a more complex model that is included both a linear and a quadratic term, just looking at a single coefficient might be misleading. For instance, this 29 cents increase, it might be the case that that's true, but only for the very first year of experience. For the second year of experience, there's going to be a different effect. For the third year, a different effect, etc., etc., etc. So how do we estimate the marginal effects when we have a quadratic term? This is something that I mentioned before as well, which is, number one, because you have now a quadratic function, the marginal effects, so on how much are wages going to increase, is no longer constant and equal to the coefficient, to any of the two parameters or coefficient that you estimate. It's going to be a combination of both, and it's going to change based on which point of reference you're going to use to understand or try to measure the impact. So how do you estimate it? You start with this model, you get your partial effects, just equal to the coefficient 1. I'm going to call this alpha 1, alpha 2, plus 2 times alpha 2 experience. So just what the only thing I'm doing is obtaining the partial derivative of this function with respect to experience. Now I substitute the values, alpha 1 for 0.298, and alpha 2 for minus 0.061. So now that I have this, I can really see that the impact on wages changes a lot based on how many years of experience a person has. For somebody who is just, according to the model, who is just entering the market, the first years of experience has a huge impact on its outcome, on its returns on wages. In fact, it increases in 29 cents at the beginning. What about for somebody who has 10 years of experience? You will just substitute it here, and you will find, let's actually do that. Let's copy this, minus 2 times this 10. For somebody with 10 years of experience, the 11th year of experience would only give him 17 cents. Somebody with 20, only 5 cents. Somebody with 50, actually for that person, an additional year of experience seems to reduce the returns to experience. Okay, but all this all nice, etc. How do you do this in the data? How can you do this without having to go through all the math? This is why it's going to be important for you to include this expression, meaning adding the C dot in front of the variable, because when you do this, Stata will understand that what you're trying to model is something like this. And how do you estimate the marginal effects? You literally tell Stata, I want to estimate the margins on how Y changes when X changes, and the only variable that I'm interested right now in estimating the change is on experience. So the marginal effects of wages with respect to experience is this. Now this is for who? This is going to be for the average person. I could have, however, obtained the same number by simply applying the formula that I had before. The coefficients of the betas, the coefficient of the beta square, and substituting the expected number of years of experience for the average person. And I should be obtaining, except for rounding errors, the same result as margin sketching. Now, once again, this happens only because Stata understands that I'm creating this interaction in my regression analysis. If you have experience with R, for example, R allows you to include other kinds of transformations in the same line. Stata doesn't. Stata only understands simple interactions. At least natively only understands simple interactions. Why? Well, the other way that you could have estimated the same model would have been to create experience square first and then include it in your model. But if you do that and you try to obtain the margin with respect to experience, it would only give you the coefficient of experience, because Stata doesn't understand that experience and experience square are interrelated to each other. However, if you're really curious on how this works and how to make it better, I wrote a small do file that you can get from SSC, and there is also a paper that tells you you can actually still let Stata understand that this is an interaction and use margins to get marginal effects for quadratic functional forms without using the C dot, etc. it's a nice exercise. If at some point you want to do marginal effects for a more complicated models, might be useful. For now, forget about this. Stick with making sure that you're making the interactions directly at the beginning of the model, or rather when your model is being estimated. Now that we have introduced the idea of quadratic effects again, it's important to understand that the reason why we're including these quadratic effects is twofold. Number one is to allow for more flexibility in the model, just because we always want to capture non-linearities in a model, but not always, but it's preferable to capture non-linearities because they always exist. But the other one might be because there is a theoretical reason why you believe there should be a non-linearity. The example that I gave you last week, for instance, was related to the idea that, what was this? If you want to model diminishing marginal returns of consumption or of utilities, or diminishing marginal returns in terms of consumption of income and savings, etc., you would like to model that in your model by adding a quadratic term. So using that, making the model more flexible, and then you can have better predictions for a particular individual. The other way to think about it is because I want to figure out something on the model that might be related to a theory. In the example that we just ran, for instance, we might be interested in finding an inflection point, which is going to be the point at which people reach the maximum returns to experience based on their year profile. The estimation of the inflection point is nothing else but math, so I'm not going to explain how do you obtain this solution. But according to this, if somebody has approximately 24.4 years of experience, that's the point where a person will reach wage possible, or if you prefer, where the marginal effect is 0. Which also means any addition according to this model, and according to assuming that the quadratic model is capturing reality the best way possible, in average, if a person has more than 24.4 years of experience, any additional year of experience will start to reduce the year wages. So we have a negative marginal effect on the year wages. Now, does it mean that the return to experience is negative after 24 years? The model says that, but it might not necessarily be the case. It all depends on how important is this point for the sample. What do I mean with that? Anytime that you add a quadratic term in a model, you will always have this parabolic function. It's always going to, there is always going to be some inflection point after which returns decline. Always, either decline or it could be an increasing function. So it's always going to be either have a function like this or have a function like this. Now, this inflection point is going to be relevant for your analysis, or in this case, this one, only if you have data on both sides of the inflection point. In this example, is this inflection point important? If I go to the scatter plot that I generated before, the inflection point falls around here. So at least 50% of the population, at least that's what it looks like, has more than 24 years or 22.4 years of experience, or 24.4 years of experience. Therefore, finding this inflection point must be important or might be important for the analysis of this data. However, and I think I have an example of that later, if the inflection point would have been around here, would it matter that after that you have a negative returns to experience? No, or probably not, because in your data, nobody would have more than 50 years of experience. So the points beyond the inflection point are meaningless for your analysis. So once again, the warning about using quadratic terms. Every time that you have a quadratic term, you have to avoid the reaction of trying to interpret individual coefficients on their own. You can't. The only thing that you can say is, at some point, increasing number of rooms may have a negative relationship with prices, but after a certain level, it's going to increase. So what it means, probably the relationship between prices and room seems to be something like this. But at this inflection point, because there is a certain, until a certain level that the return is negative, is so low that there are no observations that fall in this area. So the fact that it's negative might be the case if we would have a scenario where number of rooms is extremely small. But is that number realistic for our analysis? Let's see. In this case, for this example, where I'm trying to relate the log of prices as a function of the log of contamination, the log of distance, the log of teacher student ratio, etc., I find that the inflection point was 4 rooms, 4.4 rooms in the data. So if the houses in average, they have less than 4 rooms, for those going from, let's say, from 1 room to 2 room, from a 1 room house to a 2 room house, you would expect that the price of the house will be falling. However, for this particular case, only 1% of the observations had less than 4.4 rooms in their houses. In other words, how many observations are below here is 1%. And this is too small to say anything about these guys here. The only thing that will be important is the increasing part of the curve that is on the right of the inflection point. And for that section, let's say going from 5 to 6 rooms, is that we can estimate what is the predicted change on the price of the house. In this example, going from 5 to 6 increases the price of the house in about 7%. Going from 6 to 7 increases in about 20%. Okay, so now you know how to use quadratic terms, at least I hope you do. And you also know how to use log functions to get elasticities. What do I mean with that? Let's assume that this doesn't exist. This beta 1 coefficient is capturing the elasticity, the price elasticity to contamination, or price elasticity to pollution. This model, again, if I ignore this, would also assume that the elasticity of pollution to house prices is basically a constant. It's relative, but still that relative relationship is imposed to be constant based on this model. That doesn't need to be the case. We could make it even more flexible and say, I'm going to include not only the log of contamination, the log of NOx, but also the log of NOx squared. So just in case, oops, this is the log of NOx squared, which is different from the log of NOx squared. So this is what I'm including right now. So with that, what are the changes? Well, we can still estimate my price to pollution elasticity, with the difference now that my elasticity would also be changing based on the level of contamination.
So, Professor, for predicting the next year's effect of pollution, so should we include the log also the square, or should we just include the square for pollution?
Could you repeat the question, please?
I mean, for predicting the next year's effect of pollution, so do we have to include this square for both log and NOx, or for? or only for pollution?
That's a good question, and it's up to you really, because what you're saying is, do we always need to include this term in our models, right?
Yeah, yes.
So the answer is, if you think it's important, include it. If you're going to make predictions, most likely you need to include it, because for predictions, you want the most accurate, you want to have the most accurate result from your data. So probably having a more flexible specification will improve your model most of the time. The alternative, however, is that you probably want to test whether or not it's important to add this to the model. And I'm going to show you in a second why it's important to test this, because adding quadratic, cubic, and other terms might create a different kind of problem in your data. Nevertheless, something else that might come up if you read about this kind of material before, most of the time, if we include the logs of something, we do not include this most of the time, except for production models. If you look into the literature and look into what translog production functions are, they try to include square and interactions of variables that are already in logs. And the idea for that is to obtain a functional form that is sufficiently flexible to make predictions in terms of the production of firms, not only in that point, but predictions outside of the sample. So that perhaps might answer your question. When you should do it, when the theory or when you think that you need more flexibility in your model. But if you add that to your model, you have to keep that anytime that you do a prediction.
Professor, my question was like, do we have to square the log also for predicting the next year's effect of pollution, or no?
Yes. Yes, you have to, because once I square this becomes a function of this, right? So if you change this, you also have to change this other. Consider this. And I'm just changing the name. Instead of writing log of x, I'm just saying x1. If x1 changes, then you also need to change it to an x1 squared. So it's the same idea with the log squared. If the log changes, the log squared will also have to change.
Okay, got it.
So similarly, because we can combine square terms with log functions, you could also try using other kind of polynomials, cubics, quartics, etc. But these are often ignored because of prediction stability and interpretability, meaning we can usually have an idea what exactly it means to have a square parameter that is positive or negative. That it means either an increasing returns to scale or a decreasing returns to scale. An increasing, that's a function is going to be increasing the higher the value is or decreasing. When you have cubic terms, the curve becomes so complex that it's going to be very hard to figure out what's the direction just by looking at the coefficients. So because of that, is that models that have more than square parameters are usually not common in the literature, unless you go into semi-parametric analysis, which we are not going to talk about in this course, except for this caveat. In those cases, you might want to add more flexibility, but still you need to be careful about how much flexibility you can afford. There is a sweet spot between flexibility and how much information you have in your data that would allow you to add something like this. Now, what's the problem of adding square parameters? First of all, when you have a square parameter, I would recommend you to avoid the need reaction of looking at particular t-statistics when you have your level and your parameter in squares, or you prefer x and log of x log of x squared, you have something like this. Avoid the need of just looking at the individual parameters and say whether or not they are significant. And the reason for that is because by introducing polynomials, you're also introducing collinearity, always. And I'm not sure if you remember, for example, and let me go with the model over here. So let me create the experience square manually. And then regress wages, experience, and experience square. So something I mentioned some time ago was that one way to evaluate how much multicollinearity you have is just to obtain the BIF parameter, which is the variance inflation factor. How do you do it in Stata? After you create your model, you just say stat BIF and just look at how large this variable is going to be. The rule of thumb tends to be equal to 10. In this case, it's above the rule of thumb. But these variables are special because they are correlated to each other by construction. So let's see if I go a little bit higher and say I want to include not only a quadratic term, but also a cubic term and see what happens. Notice that, well, number one, the last term is starting to be not significant. But if I do this, the BIFs are really exploding because the more variable or the more polynomials we're including, the higher is going to be the level of correlation within these variables. I mean, you can see that straightforward if you just do something like expert 2 versus expert. You can see that they are highly correlated. And the correlation is not going to disappear. And in fact, it's going to become even stronger if I start including polynomials of higher order. So why is that important? One of the consequences of multicollinearity, assuming that you can still estimate your model, is that your variances increase. And if your variances increase, your t-statistics are going to decline, which means that by just adding polynomials, you may run the risk of getting results that appear to be non-significant, even though the variable itself is important for your model. In the example I have here, by the way, this is the main reason why I created the Fry use, because this dataset, EconMath, is not available using VCUs. So I had to download the data, all the datasets from this link over here. But now you can also upload it automatically using the command I gave you. So in this case, the idea is to relate. Let's check this out, since I don't remember what exactly the variables are. So I use EconMath here. Try the score, work, GPA, ACP. Okay, so the model that we are trying to do right now is to try to figure out the score, the course score. So in average, how good, what has the performance of a student as a function on how many hours that person worked per week. So how much time he was working on a paid job, so which was related to how much less time he has to study, and what was his performance during high school based on his GPA or based on the ACT as a, well, he says a composite. I'm guessing this is going to be a dummy that says 1 if he passes ACT or not. So in theory, you should expect that people with higher GPA will have better score because they were better prepared. They were good students in high school. Then most likely they're going to have a good score right now, either in college, etc. ACT, in this case, contrary to the evidence we had from a previous exercise, it seems that if the person passes ACT exam, his score should also be higher. Now, what about work? If work tells you how much time a person is spending on their paid job, it would also imply that there is less time that they are spending studying. And if that's the case, the more people work, the worse should be their returns. And that is what this model is actually telling you, both in terms of the coefficient of work itself and work square. But when you look at the t-statistics, the p-values or the confidence intervals, you see that in all cases, 0 falls here, meaning that you will run the null hypothesis that the beta work is equal to 0, or that the beta work at a second hypothesis, beta work square is equal to 0. You cannot reject those null hypotheses. So you would mistakenly say that even though work has a negative effect on the score, they are statistically not significant, and incorrectly conclude that it doesn't matter if people have jobs, it's not going to affect their score. And that would be incorrect. Why is this going to be incorrect? Because by introducing work and work square, we are also introducing multicollinearity, which is going to affect how standard errors are estimated, which is going to affect the t-statistics, the p-values, and how significant they are. So what's the alternative? The alternative would be to run a joint hypothesis of whether work and work square are both simultaneously equal to 0. So is that the case? I actually run this, and you can do that both ways, either using the t-test like I did right now, or using the f-statistic construction as I mentioned last week. And you should find that according to the evidence in the model, you reject the null hypothesis that these two coefficients are simultaneously equal to 0. So it's possible that sometimes one is 0, sometimes the other is 0, but adjoint, they have an impact on the scores. Now, what's the impact? You would like to estimate margins to figure out, in average, how much worse their performance is for each additional hour of work. So actually, we can do that over here. Let's see, regress score of work and work square. And this tells me that for each additional hour of work, the score is going to decline in 0.2, and this effect is statistically significant, which is different from what the individual coefficients would tell. Yeah, so for each additional hour of work, and keep in mind that according to this, the average number of hours people work is 8 hours. I would say that this is 8 hours per week. An additional hour of work declines the score in 0.20, and the average score was 72. So conclusion, and this is actually very interesting, an additional hour of work does have a statistically significant impact, reducing the score, but the overall impact is actually quite small for one additional hour when you compare it to the average. However, when you compare it, and let me see if my guess is correct, keep in mind that almost 43 people in this sample do no work, And when they do work, they have to work at least, in average, 15 hours per week, which means that when we compare people who work versus those who don't, a better characterization of the impact should be to multiply this marginal effect for one additional hour of work times how much time people who work had to dedicate to that in average. So you lose 3 points, 3.3 points in average over a 100-point score. Is that significant? I would say it would really depend in which point of the distribution you are. If you are on the higher end, probably doesn't matter. If you are in the lower end, this would be the difference between passing or failing your class.
Professor, why did you equalize it to 0? Does it mean people who doesn't work?
This?
Yeah.
So what I was trying to do is have an idea of the distribution of number of hours of work, right? Another way of looking at it would have been this. What you're seeing here is that a lot of people work, but there are a lot who do not work. So if I want to measure what's the impact of hours of work, something that I believe to be better would be to estimate how many hours people work when they are working. That's why I do this. So this is the number of hours in average that people who are working work. They work between 3 to 37 hours per week, but in average, they work 15 hours. That's why I was doing that.
Okay, and in the slide that you run a test, if a statistics test, can you just briefly again tell what that's meant?
Yeah, absolutely. So let me re-estimate the model. So this is the model that I was running originally, the same one that I have here. How do you know if variables are significant? Usually you just look at the p-values, the t-statistics, or the confidence intervals, correct?
Yes.
And according to the single t-statistics or single p-values, work and work square are non-statistically significant. So if you just look into this single t or this single p, you will conclude work has no impact on the student's performance. But is that true? What I'm trying to say here is it might be true, but it also might be incorrect, because the reason why these coefficients are non-significant is because of the problem of multicollinearity between work and work square. So how do we test for that? We have to simultaneously test if work is equal to 0 and if work squared is equal to 0. So you have to run a joint hypothesis of two different conditions for the coefficients. And this is what this is telling me. These two hypotheses are rejected based on the evidence of my data at almost zero probability, a zero level of confidence interval. Is that clear?
Yes, it's clear now.
Perfect. Okay. So now that we know how to use quadratic terms, we can take a step further and use also interactions. Now, why interactions are going to be important? Consider again this model that I have here. Prices as a function of the square feet of the house and the number of bedrooms, plus an error. So let's assume that this is the model that I'm interested in, and I run this model. What this model is telling me is that the impact on the size of the house and the number of bedrooms of the house, how these variables move, is going to be completely independent from each other when you're trying to measure the impact on the price of the house. which basically means that if the house is very big, it doesn't matter how many bedrooms it has, the price is going to be high, assuming that the effect is positive. And it doesn't matter how big the house is, the more bedrooms it has, the higher is going to be the price. But is that idea correct? Is that idea sensible for all cases? Probably not. You want a balance between how big the house is and how many bedrooms they have. So you need to allow for that interaction in your model. Perhaps a more realistic example or something more practical that you might be familiar with would be in cases of wages. You know that higher levels of education will provide you with better wages, but you also know that men and women are going to be treated differently in the market, and they are going to have different returns to their, just because they are men or women. They're going to be treated differently. Women are most likely going to be discriminated against and earn lower wages. But it is possible that there is also a double combination, meaning that it doesn't matter if a woman has a high level of education, her level of education is still receiving a lower return than men. So you need to allow for that interaction explicitly in the model. How do you do that? By adding interactions. In this case, I'm saying that the price of the house depends not only on the size of the house and the bedroom, but also the combinations of the bedroom and the size of the house, plus bathrooms. Now, by doing this, however, you need to again be aware that the marginal effect will no longer be a single number, because similar to the case with the quadratic components, it will change depending on the variable that are interacting. For example, if I would like to know what is the return or how much more I have to pay for an additional bedroom, I first need to know how big the house is. If the house is too small, very likely that I might have to pay less for an additional bedroom, because it would mean that each bedroom is increasingly smaller. But if the house is in general large, probably I will have to pay an additional premium for another bedroom to be constructed, or to have access to another bedroom in that house. It is true, however, that this coefficient can still be interpreted on its own, but the interpretation is a little bit off, because this coefficient would be how much I'm willing to pay for additional house for the house, assuming that the square feet is equal to 0. Now, is that realistic? The answer would be no. Therefore, you cannot make interpretations on this coefficient on their own. So, again, one of the problems of using interactions, at least when you're starting to use interactions in your standard modeling, is that they become difficult to easily interpret. Easily interpret in the sense of you cannot just look at the number and make interpretations out of them. So what's the alternative? You can do what is called a reparametrization of all the interaction terms. This reparametrization basically means that for these interactions, instead of using the interactions themselves, I'm going to use interactions that have been slightly shifted. You know that shifting a variable has no impact on the outcome, and I can shift them in such a way that in average, the impact of this is going to be equal to 0, and if the impact of this is equal to 0, I can recover the interpretation of the original coefficient. So what are going to be the advantages of reparametrization? Easy interpretation, because you do not need to estimate these marginal effects, unless you have the software, of course, that we're going to have, but you will not need to estimate those marginal effects. Standard errors are already available. You do not need to estimate them, or nor ask your software to estimate them. And if necessary, these interactions can be centered not only at the means, but at any point of interest that you may have. So you're not interested on the average house, you're interested on the house with 5 bedrooms and with 20,000 square feet of footage. You can recenter the valuables in those particular points and still have a reasonable interpretation of this coefficient for that particular case. And this can also be used for other functional forms, meaning doesn't matter if they are interactions, logs, etc. They can be used for all further. Doesn't matter if you have quadratic, cubic, or further polynomial terms. You can still use them for this kind of interpretation in terms of the marginal effects or the interaction of the effects. So a couple of examples. I think I forgot to update this other one. So I'm going to do this live because I forgot to do the update on the slides. So let's go first on this one for the returns to 2 hours of work as we had before. So the first thing in order to do the interpretation of work using this reparametrization would be to center the variable of work. If you would like to do this in a step-by-step process, you would have to first do the summary of work. This would give you the mean. And then generate a new variable, C work, for example, that is equal to the older one minus its mean. Now, this command automatically does that and gives you this new variable. If you apply this in your own your computers, you're going to see that now the average of C work is equal to 0, but the variance is going to be the same as the variance of work. So we're doing just this shifting of the variable. And now here, instead of interacting work, I'm going to interact C work. Now this is going to be important because if I take the expected value of C work, or if I evaluate this at the expected value or at the means, the means of C work is equal to 0. So this effect at the means is going to be equal to 0. Now, what exactly this means for us? That by just using C work, the coefficient that I'm going to obtain in my regression is already interpretable, and is the same one that I had that we estimated before. That for the average person, an additional hour of work reduces their score in 0.22 decimals. Now for the other one, which was prices, okay. Housing prices. So Rios, actually price 1, clear. The original model is prices as a function of bedroom, the square feet, and the interaction between bedroom and square feet. So notice that because these variables are continuous, I still need to use the C dot to do the multiplication of both of them, using the pound function to do that multiplication. So I do all of these, and if I want to interpret the marginal effects, I will have to choose for which point of the distribution I want it, or if I want to do this for everyone and get the average. And the individual coefficients are not interpretable. For example, it doesn't really make sense that an additional room will generate a negative or a decline from the price of the house, or that the square feet, an additional, if the square footage of the house increases, that it will have no statistical impact on the price of the house. So as I mentioned before, we should first center the variables. So I can use the command center, bedrooms, square feet. We created these two additional variables that I'm going to use only for the interaction. And now we have results that are more sensible, or at least closer to what we would expect. On the one hand, an additional bedroom in the house increases the price of the house in about $11,000. Even though this effect is not statistically significant, and in average, or for the average house, an additional footage or an additional foot or a square foot on the footage of the house increases the price in about $116 approximately, which is statistically significant and was not originally seen as such for the previous model. Other than that, because I'm just using an affine transformation, the R squares remain exactly the same. And as an additional point, and just to make sure that, or to show you that this actually works, I could have just as well do this and ask Stata to construct the variables automatically and give them to me. And by doing that, I obtain the same results as I would using the manual approach, which is one additional bedroom increases the price of the house in about $11,000, and each additional foot of the house footage increases the price in about $116. And I say in that way because if we describe the prices, is measuring the house prices in thousands of dollars. Further issues. So one of the things that now might become a problem, and not necessarily a problem, but something to be aware of when you have interactions, quadratic terms, or even just using logs, is that the marginal effects will now change based on the values that you're trying to estimate these for. What I did previously, for instance, all these, the marginal effects that I'm estimating right now, these ones, to obtain this value or this value, are valid only for the average house. The average house that has whatever number of bedrooms there are, or for whatever number of the average square footage you have. Which means that you have a house that is larger or smaller in terms of the bedrooms or square footage, the marginal effects for that particular house is going to be different. Which also means that your marginal effects will depend on which values you're using or which value you're trying to evaluate. Which is all good and fine. You can always estimate this for every single case in your data and just report it and try to analyze for all the subjects in your sample, just say what would happen for each one of them. However, most of the time we're going to be interested in reporting only one value that represents everyone. And if you want to do that, there are two preferred approaches to do that. You can either report the average partial effects or report the partial effects at the means. The only difference between those is how to estimate that number that represents everything. The average partial effects, APE, or as I write it here, PAE, is literally telling you that you should estimate the marginal effects for every single person in your sample, and then just average this for everyone. Now, these people suggest that this is the best approach, especially for nonlinear models, because it has a more balanced representation for everyone. The alternate approach is going to be to estimate the marginal effects at some means or at some other variables of interest. one of the most typical examples would be, for instance, to estimate this marginal effect for the average person, evaluating the excess at the excess of that non-existent average person. For most of the models that we have seen, certainly for the models without interactions, but also for the models with single interactions, only quadratic terms, these two approaches will give you exactly the same result. However, when you go to other kind of models, nonlinear models, or models with cubic interactions, triple interactions, etc., these two are no longer going to be the same. Which one would you prefer? It really depends on what do you think is the most representative point for your sample. If you believe that talking about the average person is better, you can stick to estimating the MEMS. If you believe that averaging the effects for everyone is better, you can stick to estimating the pi, or the average partial effects. In Stata, when we did margins, it was actually it was already estimating the average marginal effects or average partial effects, the pi. You could request, however, to estimate the average effects at the means. And what is going to happen in the background is that rather than estimating the effects for every single household and then obtaining the average across all of them, is this estimates the average effect for only for one household, assuming that that household has these characteristics: 3.6 bedrooms and 2,1300.7 square feet and footage. Some other things to consider. Remark on the R-squares. Something that I mentioned last week is that the R-square is really a measure on how much variation is being explained. Now, one of the disadvantages of the R-square is that the more data that you have, or the more variables that you include in the model, the higher the R-square is going to be, which sometimes people assume that means that your model is going to be better. But that is not necessarily the case. As I explained a few times, having a higher square doesn't mean that your model can be interpreted as causal. And having a lower square doesn't say that your model has no potential power. It only suggests perhaps that having a lower square will provide very bad predictions if you would like to use your model for predicted purposes. But that's it. Now, because the R-square is always increasing when you add more variables, it is not going to be the best approach to tell people how good your model is to explaining the data, because it's possible that a lot of the gains that you're getting are just because you're having more data included to the model. Because of that is that we can, instead of using the R-square, we can use the adjusted R-square. Again, the motivation of the adjusted R-square is going to be to avoid misleading conclusions that just adding more variables in the model will always make it better. Now, this is a question that I had last year. I'm not going to ask this again, but just as a reference, the R-square can never go down, and it usually increases for almost all cases unless your sample size changes. So just to keep that in mind. So how do we adjust the R-square so it doesn't always increase the more we have, the more variables we add? Well, we add a penalty. And the way to add a penalty is to say that the numerator of the model, which is trying to measure how much is left unexplained, will have to be inflated for the fact that you're using more explanatory variables. This also implies that there is this close relationship between the adjusted R-square and the regular R-square, and therefore the adjusted R-square is always going to be smaller than the regular one. Furthermore, the adjusted R-square can now be used to compare models that are nested, or either models that are not nested, but you want to compare just how good they are in explaining the variation in your model. For example, let's say we have this scenario with two not nested models. They're going to be not nested because the only variable that is on model one is not included on the second one, and these variables are not included in the first one, so therefore they are not nested. There is no way to make one model look like the other. Normally, there is no way to compare them and see which one does better. The second model here might look better based on the R-square just because by adding an additional variable, we have a higher R-square. The better approach, however, will be not to look into the regular R-square, but look into the adjusted R-square. In this case, both the regular and the adjusted R-square increases or is higher for the second model, which will make you conclude that this model is better in explaining the data compared to this other model.
So what's the difference, Professor, between adjusted R-square and R-square?
The main difference is the adjusted R-square penalizes the fact that you're using, or that you may want to include more variables to explain the model. So remember, what happens when you add more variables in your model? Your R-square increases. So if somebody tells you, please make this model better, they might ask you, why don't you just add more variables to increase or to improve the quality of your model? If it always looks like adding more variables will make the model better, we have higher R-square. To avoid that problem is that you should use the adjusted R-square, which add this penalty term, which basically implies that every time that you add more variables to the model, your adjusted R-square will not necessarily increase. It might sometimes decrease, because instead of improving the quality of the model, you are diluting the results. So the main difference is you have a penalty, and this penalty allows you to put a balance to not just add garbage in terms of explanatory variables in your model. Is that clear?
Yes, thank you.
You're welcome. Okay, so the adjusted R-square can be used to compare models like these that are not nested, by just looking at which one has more predictive power. There are other methods that can be used also to test for whether or not to model which one of these two models are better. I'm not sure if I include that here, but you can look into the on Wilbridge. It has a procedure to test two non-nested models. But what I want to emphasize here is that I can still compare these two models using the adjusted R-square, because these two models are explaining the same dependent variable. So they are related to some extent. Something that cannot be done, however, is trying to compare two models using the R-square when the models are different. In this case, for instance, I cannot compare a model that has salary as my dependent variable to another that has log of salary as my dependent variable. Among other reasons, because I'm using logs and I'm reducing the variation, I will be artificially increasing the R-square. So in these situations, do not use the R-square to explain this. Why else is going to be so? The idea of the adjusted R-square is to try to drive you away from just adding more and more variables in your model. But there are other reasons why you have to be careful about adding too many factors in your regression analysis. If you recall when we covered the second class, one of the reasons why we like to introduce the idea of multiple linear regression analysis is because by adding more variables in the model, we can more strongly say we can keep this fixed whenever we are measuring the causal impact of the treatment on the outcome, right? So if we want to know what's the terms of education, I would like to control for a skill and keep a skill fixed. So when I estimate the model, education is really giving me how much the wages are going to increase because somebody is more educated, not because they are more skillful or because they are smarter, etc. So in some cases, however, in some cases, certain variables shouldn't be held fixed. And what do I mean with that? This is, if you read some of the newer literature of how they are trying to call about this, is the idea of collider bias, or as the book calls it, having the idea of this bad control. So what is going to be a bad control, or what's going to be a collider bias? The idea is to avoid variables that might inadvertently absorb the impact of the variables of interest. And for that, perhaps it's going to be better to go to a very simple example. Let's say that we're trying to analyze the impact of attacks on peers and what's the impact on traffic fatalities. So that's our purpose. You have been hired by the state of New York, let's say, who is thinking about increasing the tax on beer and see what's the impact on fatalities. And I'm asking you to figure out what's going to be that impact, to tell them if it would be a good idea, bad idea, etc. If that's the case, the question is, should you control, for example, as part of your control models, should you control for the consumption of beer? Normally, you would say, yes, let's just put everything and let's see if the taxes still has any impact on traffic fatalities. But why is the reason that we are thinking about the state beer to have an impact on traffic fatalities? The reason why it might have an impact is because we are hoping that the higher level of taxes will reduce the chances of people consuming more beer. So it should make them less likely, or it should make them less likely to be drunk because they're consuming less beer because beer is more expensive, and that is what should reduce the level of fatality. Therefore, you control directly for beer consumption. You are taking all that. You're taking the channel directly from what you were trying to estimate as the causal effect of your treatment. So your treatment is a state beer tax. The channel that is affecting fatalities is to consumption. And if you include consumption as your control variables, nothing will come up as part of your state or as part of your taxes. So state consumption of beer in this case is either a collided bias because it's affected by your treatment, or it's a bad control because it's affected by the treatment, and that's the reason why fatalities occur. Another way of thinking about this, in a regression of family health expenditures on pesticides, if you would like to measure, for example, what is the impact of pesticides, what's the regression family expenditure on pesticides? I think this was the other way around. So if I would like to measure the impact of pesticides on family health expenditure, I shouldn't control for doctor visits. Either I should control for doctor visits or for family health expenditure. You cannot control for both of them because pesticides is going to have an impact either by having you go to the doctor more often or by increasing how much you're expending. But if you include one or the other, the impact of pesticides might get diluted because you're absorbing some of its impact through the channel that is affecting your outcome.
So the note is that you might want to you might include regular visits or as in, might subtract out routine expenses so that you're getting them, you're showing the variable specifically.
Right. So in this case, routine visits to the doctor, those you can include, because routine visits to the doctor is going to affect expenditure, but it's not going to be affected by the use of pesticide. So you're avoiding that collider bias problem. Regular visits shouldn't be affected by pesticides. And that's something that you would like in this case. Also keep in mind that different regressions might serve different purposes, because in some scenarios, you might want to include all these variables if what you are trying to do is prediction, for example, or testing how good your prediction model is. In other words, if I do not have information on family expenditures, current information on family expenditures, but I always have information on pesticide use and the number of doctor visits, it's probably going to be good for me to add all this information if at the end of the day what I'm trying to do is predict how much a household spends on health, how much a household uses or spends on health expenditure in the future, and the only information that I have is pesticides and doctor visits. So if your model is predictive model, then it makes sense to include bad control or collider bias if that's the only information you're going to have by the time you're trying to do those predictions. But again, why is it going to be bad to include a lot of variables in your model? And some of these we already mentioned before. Adding more variables in your model is going to exacerbate problems of multicollinearity, and you have more multicollinearity, it might look like the quality of your model is declining because you won't be able to say if things are significant or not. However, adding other regressions to your model sometimes can be positive if these added regressors are for example, if what you're trying to estimate is something like the elasticity of beer consumption, and you add information that could be related to preferences, but not to prices, then you're going to have a more precise measure of the elasticity, because the impact of the coefficient or the variance of the coefficient is not going to be affected by adding more variables, because they're going to be independent from each other, and you're just reducing some of the unexplained values. Okay, something else. Predictions. And this is only going to be valid for linear regression models. Once you have your predicted model, and we start with y is equal to alpha 0 plus alpha 1, x1 plus an error, you can make predictions of the data in two ways. This is what we normally obtain, which is the predicted value for a person in average. And for this person, I can estimate what is going to be my predicted, sorry, I think I got confused around here. I apologize for that. So, once you estimate your model, you can obtain both the predictions of the model and the error of the model based on this on the sample that you have. Now, this is going to be important, or you can use this for more specialized analysis that will relate specifically on the error. And again, this is going to be related more to the idea of if, based on your model, you want to say if the predictions are good or are bad, or how close they are, if somebody's paying more or less what they should. So let me rephrase it again. let's say that we have a model that you're estimating something like prices as a function of household characteristics. You are able to obtain the predictions of how much, based on the characteristics you think a house should be valued. You could use, based from there, the errors of the prediction to decide, or at least to assess, if somebody is paying more or less than the predicted value of the house. And that is really it. Once you have the residuals, you can assess if somebody, for instance, is overpaying and underpaying, or if the performance is, if somebody is overperforming their predicted results or underperforming their predicted results. The other thing that we can get from here is that because I'm predicting not only the conditional mean, but I have some idea of the error, is that I can also use my regression results to make predictions on what do I believe the expected value of something will be. So what do I mean with the expected value of something? So let me go to the next slide. Now let me go back. So let's say that you are asked to estimate a model in which you want to estimate, somebody's asking you to estimate the potential performance in college. So we're going to call it college GPA. And the only information that you have available is their high school GPA and let's say the ACT. And this is a model that we have done before. Once you have this, something that you can use this model, and it's going to be related to Aria, what you were saying before, is what if I would like to use this model to make predictions for the future or predictions for making some decisions. So let's say I want to hire or I want to admit the best students. Can I use the predictions of this model to say something about that and to give a tool to the policymakers or to the decision board to say whether or not they should admit the student or not? So once I predict all of this and I ignore the error, I can have a point estimate for my for what I think the GPA, the potential GPA of somebody with a given high school GPA and a given ACT score is going to be. However, just like I said before, that point estimate is always going to be wrong. So the alternative is to give to the policymakers or to the person who is interested on this information, is to give them some confidence interval on how precise you think this is going to be, how precise this predicted value will be for the person or for somebody who has this kind of information. Doing that is relatively simple because the only thing that you need to do is to substitute all the values for a particular person of interest. So given certain characteristics, obtain those predictions, and then just estimate the variance given those values and the estimated coefficients. This will give me the confidence interval for the expected value of y. The expected value of y in this case is just, in average, what do you think is going to be the range of the scores that people with these characteristics are going to have? Some other times, however, you might be asked that you don't care so much about the variance, you really care about all the possible, to provide some range for all the possible values that people with these characteristics might have. So in this case, what they are asking is to provide a measure of confidence, not on the predicted value, but on the predicted value plus the error. So they want to know how much you should trust this value and give them a confidence interval for that. This is also simple, although not as easy to apply in the, I'm actually asking to Stata to give me an answer to how to do this much easily. But from the mathematical point of view, it's relatively simple, because what you're trying to say is that the variance of the outcome has to be a combination of the variance of the prediction plus the variance of the error. And this confidence interval for the predicted one is simply going to be much larger than the confidence interval that you would get just for the expected value of y. Now, if I would like to do this again for a couple of different people. So the same example as I was saying, here I'm assuming that that I was interested in estimating the college GPA, and the information that I have available are the SAT scores. I think this was the high school percentile, so how well they perform in high school based on the records that we have access to, and what is the size of their households. At this point, I don't think I have a theory why would the size of the household would matter for this model, but let's assume that it matters based on some underlying theory, etc. Now, let's say that you want to estimate what is the predicted value for somebody who has an excellent SAT score, a decent percentile on their high school returns, and has a relatively large household. I can use margins to produce what's the predicted value of the GPA score given these characteristics, and what is the confidence interval of this expected value. So this number that you obtain here is equivalent to this, to try to provide this confidence interval to what I believe the mean is going to be. If I would like to do it for a different person, somebody with a lower GPA, lower high school percentile, but a smaller household size, I can do the same. Then in the state, I want to estimate the margins at these values, and it's going to give me this other number. So according to this, if I could have to compare what is the predicted score between individuals with these characteristics, it does seem that the first one, and probably because of the higher SAT score, will perform better in college compared to the second one. At least in average, you should expect them to perform better. A trick that can be used, however, is to use the same kind of reparameterization that I mentioned before, to have the same kind of predicted value for the for what you expect the average to be for somebody with certain characteristics. So how would I do this reparameterization? I can recreate new variables by just transforming the characteristics and centering them at the values of interest. So what I had before here was that I wanted to estimate the predicted values for somebody with these characteristics. And instead of doing that, what I'm doing here is transforming all of that by creating new variables centered at exactly these values. So after I have all of this, I estimate my model. I don't care about these coefficients because these are just, well, I'm not going to interpret those coefficients. The only thing I'm interested in is what happens with the constant. Now, if you remember, the idea of the constant is to provide you a prediction on what would happen when all the values, all the variables in your model are equal to 0, right? And all these values are going to be equal to 0 only for a person that has an SAT score of 900, a high school percentile of 20, and lives in a household of 3. So for that person, the predicted college GPA is 2.4252. And if you look at this is exactly the same as what I would get using margins. So it's just a different way to get the exactly same result. Now, the other component that I'm missing from here is how to obtain the predictions or the confidence interval for the predicted rather than the expected value. And I'm owing you this because as far as I know, there is no easy way to create this automatically from Stata, but I'm asking them directly. So if they give me an answer, I'm going to give you one. Otherwise, I'm going to write a small code that does this for you. Okay. Now, this is the last thing. It's something that I mentioned before, and it's what happens when you use logs as dependent variable. As I mentioned, using logs as dependent variable, it's something that a lot of people do because it really simplifies the interpretation of your coefficients, at least in economics, because people like to talk about elasticities and semi-elasticities and relative changes. The problem happens if you want to use that model to make predictions. It becomes much more difficult to do so because making the transformation from log to the original data, given your model predictions, is not straightforward. So let's say that we do that, and why is this a problem? So we start with estimating a simple log linear model and say we're going to do our regress of log of wages as a function of education, experience, etc. How I then obtain a predicted value for y? Something that people usually do is just saying y hat should be equal to the exponential or the beta of all of these, ignoring the error term. Ignoring the error term, however, is going to be incorrect because the error term is part of the model itself, and you cannot just zero it out. In fact, if this is your original model and you want to recreate this, you really have to exponentiate everything. But normally, when people do this, they only exponentiate this part of the regression. So what we are missing is this. If we can make an estimation for this component, we can make predictions of a log linear model. So there are going to be three options that you can use to make this kind of prediction. And these three options are going to depend a lot on the assumptions that we apply to the model. If you want to believe that the model that you estimated had errors that were normal, so if we want to say this error follows a normal distribution, normal, then your best approach is going to be to say that this expression that we do not have access to, this one, is equal to just the exponentiation of sigma divided by 2. Because we know that the assumption of normality doesn't always hold, you can be a little bit more pragmatical and say, rather than estimating this with a formula, I can just estimate it based on all the data in my model, which means I first will have to obtain the residuals for all the observations in my data, get the exponentiated residuals, and then get the average of all of these. I use that as my approximation for what I do not have in my regression. The last option is to be even more practical and say that I will just run a regression of my original variable against my predicted but incorrect predictions on my data in a model without a constant. So in this case, this parameter alpha will become my approximation for this element that is missing when we are trying to do the prediction of the data. Now, once you have this, your R-square estimation is straightforward. So in addition to be able to make predictions using a log linear model, you can also use this approach to obtain an R-square, a pseudo R-square that is comparable to the standard R-square. These, of course, are going to be different from your adjusted R-square. So for now, we are going to forget about this. This is only to create a pseudo R-square that you could use to compare it to the standard R-square to see if one or two models that have different dependent variables are comparable to each other, or which one is better than the other. So how do I do this in this data? For this, I'm using a different data set, and I'm running my regression with a log wages as my dependent variable. Now here and here, what I'm doing is making the predictions of the betas times x's. That would give me the log, the predicted log of wages, and I'm also getting the predictions of the residuals. And ideally, or by construction, the original log wages are going to be a function of the predictions plus the residuals. So the next step that I have here are just approximations from these three approaches that I described here. So the first one says, under normality, just estimate the variance divided by 2 and get the exponential of that. So I get my residual, do summary statistic, get the variance divided by 2, exponentiate it, and multiply that to the exponentiated of my linear prediction. So wage hat 1. The second says, be a little bit more empirical, get the residuals, exponentiate them, and get the average. I have my residuals, I exponentiate them, get the summary statistic, and use the average. This gives me the second approach for the predictions. Number 3, it says, run a regression of the original variable versus the exponentiated prediction of your model, and use the slope of the model as your explanation as your approximation for the exponentiation of the parameter that we do not have access to. So I run my regression of the original wages against the exponentiation of my predictions with theta constant. My third prediction of wages is just wages times that slope. So just as a comparison, I give you here all the predictions. This is the original. These are all the other alternatives. And as you can see, they are going to be off. So that the relationship of the predictions and the expected values is no longer there, but they are much closer compared to if you were to just look at this parameter over here. What about the R-square? For the R-square, you will have to use a little program that I wrote, and you can copy this. And if it doesn't run for you, let me know so I can send you the do file, where I'm just creating new variables that replicate the function that I described before. All of that is to replicate this little statistic that you have here. And from my three alternatives, it seems that the one that fits better the data or that provides you the highest pseudo R-square is the last one. but the difference between all of them is just marginal. And something else, and I think I can show you that clearly on this data. The model was wages as a function of education, experience, tenure, and blood. So notice here that in this model with levels, the R-squared that I'm getting is 0.16, 61. That is actually higher than the model if I happen to use the log linear model. However, if I would have gone and use the log wages, you would have seen that this alternative modeling was better because it had a higher R-squared. But again, you shouldn't use the R-squared to compare these two models because the dependent variables are different. But I can use the R-squared that I created here to compare it to the original linear model and decide which one has a better fit on the data. Okay, that's everything that I have for today. Are there any questions? If there are no questions, just as a reminder, your homework is due tomorrow at 5. If you have any reason why you think you're not going to be able to reach the deadline tomorrow, please let me know today by the end of the day, so you can have an extension. Not just, well, give me a justifiable reason why you might not be able to do it, to present it tomorrow. Otherwise, if I don't receive any information of you today, not tomorrow, I'm going to assume that you didn't send your homework. And that's basically it. Next week, we start with, I can't remember what's the next topic, but let me see. Next week, we have some fun stuff. We're going to be starting some of the analysis with qualitative information, the use of dummies, and how it can be used to allow for more heterogeneity of your regressions. Okay, that will be everything for today. So if you can, again, you can go to the conference this afternoon. They are presenting very interesting papers. Unfortunately, I cannot be there for other reasons. But I might even get, if any of you see anything interesting, if you happen to go to the conference this afternoon and you want to substitute one of the examples that they give you there instead of question number 1, I will also use it as a good example of a practical terms of how to estimate causal effects. I think there are a couple of papers that are trying to do something on that direction of analyzing the impact of a program on some independent variable and justifying it in a particular way. So if you want to use that instead of the first question of the homework, that will be also quite, it will be acceptable for that. Okay, so that's it. Enjoy the rest of the day and see you next week. Bye then.